Muy buenas tardes a todos. Muchas gracias por atender esta invitación.
Ay, así que está bien.
No, está sonando.
Pero quítale el sonido.
¿Sana? No, ya no sale.
Me parece que quedó. Muchas gracias. Buenas tardes a todos. Muchas gracias por atender esta invitación. I would like to introduce Dr. Gandu. Thank you very much for sharing your knowledge and your time with our community. So, Dr. Gandu is Senior Technical Director of the BGP Optical Science and Technology Division and Senior Technical Advisor of BGP. He provides technical advice to projects of microseismic monitoring of hydraulic fracturing operation, distributed acoustic sensing, DSP survey, and 3D DSP imaging, integrated shale gas reservoir characterization, etc. CPCD. He's an active member of different associations, so the title of the speech is application of distributed fiber optical sensing in the oil and gas exploration and production. So thank you again.
You're welcome. Thank you very much to come to this talk. I'm very happy to be here. I've been to Columbia, this is my third time now, but I never come to this university. So it's a very good chance for me to know about this. And through my friends, who is a supervisor from Pluto University, he said that I'm going to be here. He wanted me to give a student talk about what we're doing in optical sensing. So if you are studying geophysics, particularly in these days for oil and gas exploration, the fiber optical sensing is new, actually about 10 years now. It's quite developing very fast. In many oil fields, many oil companies, it's being used worldwide. If you're looking at SCG and meeting, there are a lot of workshops, talks on this topic. I think there are also DAS workshop in South America as well, by ENGG or SCG. So today I will just give you a quick introduction about what BGP is doing in terms of optical sensing. We started with simple borehole seismic. But I don't want to emphasize for oil and gas development, which is the reservoir monitoring, fracking monitoring, long-term monitoring, using fiber cable. That's why my title is not say seismic, but it says for oil and gas E&P. How do there's no remote control.
No,
manually?
we don't have it.
Okay,
So
fine.
it doesn't work with this computer.
Right. Okay. I have basically 4 parts. I'll give you a quick introduction about optical sensing. Then I talk about the borehole seismic application using fiber optic cable as geophone in the borehole. And I will talk about those monitoring applications using fiber optic cable, measure temperature, acoustic noise of fluid, and for the stimulation and production. And we have some conclusions. There's one slide, give you a little bit background study about the optical sensing, but this is particularly talking about the acoustic sensing. So this is the principle, basically the seismic wave, acoustic wave. If you study seismic, you know we have dynamite, we have vibrate, we generate the energy, we transfer to the formation, come to the receiver, geophone, the surface, in the borehole or in the sea floor. In this case, we are using a fiber cable in the borehole or in the on the surface. We could recording the seismic wave using the fiber. Geophone OBN is a discretized measurement every 5 meter, 10 meter GFO. You don't have a continuous measurement. Well, fiber is basically you can do continuous measurement. That's what I call it distributed acoustic sensing. That's a DAS from. When you have this size energy come to part of the cable in the borehole surface, this part of fiber gets stretched or compressed, very, very tiny amount. Nanometer, 1 meter fiber may be shrink by 1 nanometer, or even picometer, or stretch. And those changing of the cable itself will affect our lights, the laser light pulse coming through the cable and reflect back at every point. Because reflected light is called the Rabi backlight light. Its intensity, frequency, polarization, and the phase can be changed. Very, very small. But today, the most sensitive interrogation of the signal is a phase interrogation called 5 and the displacement of the fiber itself compared with the acoustic energy is a linear transformation. So you can easily interrogate this once it's a linear. That's why most of the seismic measurement using phase interrogate. It's called a phase optical time domain reflectometer. That's the interrogate box. You have connect the cable and then just recording. You can recording passive energy from passive seismic, microseismic. You can also recording active seismic energy. Now people use this cable in the ocean, marsh, in the earthquake. There are so many cables across the ocean for internet access. The same cable can be used for marsh in the earthquake. So this is basically when you have the peak measurement, two measurements with the time difference. If you have no energy coming to this part of fiber, you just have background noise. Your measurement is the subtraction you get basically is noise. But at this part of fiber has been deformed, you get an anomaly, that's what you measure. With this energy moving along the subsurface or along the cable, you get a time series, just like in recording inside there was a series of GFO, a line of GFO. So the only difference is we are using optical fiber measure seismic energy. For seismic, for acoustic, you measure acoustic energy. So that's just I think one slide. BCP developed its own interrogator. That's our newest version. There's some parameter here. We measure string sensitivity, which is the fiber cable changing. How sensitive we can measure it. Now we can measure up to 2 pixels around this seismic frequency. Now 1 pixel, 1 picopixel is a 1 meter long cable or fiber changing by 1 picometer. 1 picometer is 10 to minus 12 or 15, whatever. It's very, very small. And it's equivalent to 0.1 nanometer displacement of the fiber. We can measure such a small change. If you want to really convert to seismic earthquake energy, it's equivalent to -4 Richter scale earthquake energy. Now, the big earthquake you can measure what is 9, right? 9 Richter scale, which devastating, kill a lot of people. People can feel about 3 earthquake energy level. Below that, you cannot feel it, but we talk about the -4. So you really cannot measure. But today, the downhole GFO usually can measure -2 Richter scale earthquake for microseismic monitoring during the fracking operation. So we are very, very sensitive. That's why we can measure VSP. There's a very large offset source coming to the receiver. Dynamic range is actually broader than normal GFO system. With this box and the digitizer 1 gigahertz inside, we can achieve 0.1 meter spatial resolution if the cable is not longer than 5,000 meters. So that's why we have 0.2. So you know the logging is 0.15, so this is known that logging scale borehole size measurement. Of course, we can difference. So usually we output 1 meter spacing borehole site data for processing, but in actually we can really measure it. Sample rate of film control can do 1 millisecond, so we can measure very high frequency. And the response of the frequency response, seismic was on the 1 hertz to 10 kilohertz. You know, GFO today is about 300 hertz, but this is much more, and it's flat spectrum. We developed some to the low frequency LFS, which we can measure 1 millihertz. That means 10,000 seconds. The wave changing that 0.1%, within the very, very low frequency measurement, which is the mechanic force moving in the subsurface, which may crash the casing with casing deformation. Slow measurement, that's what we need the very low frequency. We have a laser source here. This source has different power level. The level we have now, we can do 50-kilometer long cable sensing with 1 box. We have a dual channel system, so basically you can put in the middle, you have 100-kilometer measurement channel system with 1 box. So that's what we have today as an interrogating box for acoustic signal. For borehole measurement, and we have to deploy the GFO circuitry like the better GFO, right? Or you put them in nodes. So the borehole sensing, so we have actually 4 types of deployment. One is we put the optical cable on the cable outside the casing, cement in behind the casing, become a permanently deploy the sensing array for seismic, for temperature measurement. And you cannot get out, it's permanently there. We can also put it inside the casing. You can measure VSP, you can measure fluid movement. We can also hang them outside the tubing. When you're producing oil and gas in tubing, you can also measure acoustic noise and the temperature outside the casing, outside tubing, at this kind of installation. Here is the show you basically what we do have an open borehole. We can have surface source or surface geophone, downhole cable installed into the horizontal section, then we can do fracking monitoring of microseismic and also downhole engineering application, which I'll show you later on. So this is the one now today. We started with downhole geophone array 1 by 1. Now we're using cable. The reason for this is downhole geophone is very expensive. The high-end ones, 3 components, 1 level, it costs $100,000 US. And the smallest one today being produced by Cell was called the MaxWave. You can only lift 100 level each time. Beyond that, it's a straight cable. So 100 level at 10 meter space, you can only measure up to 1,000 meter of the borehole range. If you have a 5,000 meter borehole, you have to move the geophone array 5 times, repeat the source 5 times to do a full borehole basic acquisition. Well, with cable, in 1 shot, you cover the whole borehole, you don't repeat them. So this is more efficient, high density data, lower cost. That's why the technology developed and involved. And also for downhole geophone, you have to be withstand for high temperature. Today, they can only sell the geophone up to 210 degrees C. We have a borehole in China, 10,000 meter deep, 260 degree temperature. We cannot buy the geophone which can stand for 300 degrees. But fiber cable, you can go 300 easily, or even 600 degree cable. It's all depend on the outside the coating material of the fiber. The fiber itself is a glass, right? Silicon is known at the 1500 degree. The coating material is the one holding its temperature reading. You use plastic. See this cable here, that's plastic in the outside the fiber for 6 degrees. If you skip the coating material, you increase the temperature rating. If you coat the fiber with the metal, aluminum, copper, gold, it can go 1,000 degree. Now people use this fiber around the jet engine, measure the jet engine temperature with the fiber. So for high temperature bulb application, this is much better even than the GFO we can get it today. So with the three different deployment of the cable, we develop different applications. So we can basically, for this application, we can do stop production, we can take out the tubing and we put the magnetic absorption and to minimize the coupling issue. You drop a cable in the vertical borehole, the borehole is about this big casing, and you have a very small cable. If they are hang in the fluid, will not have good coupling with the acoustic measurement. So we put a magnet in the cable to get the coupling, so we can do with the measurements. If we have a cable outside the casing, we can do all of this stuff apart. We can also do this measurement of the strain, which is the subsurface force. With the tap movement, hit the casing, which damages the casing. So that one, you can have a sensor outside the casing, you can measure the force in the subsurface through the production, during production, or during fracking operation. Because fracking basically inject a lot of fluid into the formation to break the rock. That force can be measured by the cable outside the casing. So that's introduction. Now I'll talk a bit about the VHP applications, what we're using cable. The reason we didn't do surface seismic is this. For GFO, vertical GFO, you will not recording horizontal component, right? The relationship between incident angle and the GFO orientation is the cosine theta. When theta equal to 0, you get the maximum response for vertical GFO or horizontal GFO. But if it's between, it's a cosine theta. So with 90-degree energy, vertical GFO will not recording. Same with the cable, but it's a cosine theta squared. So at the 0-degree, 90-degree, it's the same as GFO. But the between is a slight difference. So if you put a straight cable on the surface, the reflection data come to the cable is a very large angle. You'll not be able to measure it at the 90-degree. So we don't use straight cable to reflection seismic. People use it to what? To this surface wave measurement. The circulating polarized surface wave can be measured by the horizontal cable, but not reflection. So the start with this one, we really go for borehole seismic. But today now there's called S-DAS. People are doing this measurement with large outside source when you come in. It's not the vertical angle, it's a little bit 45 degree. But initially it was really developed for borehole seismic. Okay, the advantage of this VHP surveys in cable is high density, and that's what we can do on the 1 meter measurement along the cable. But the GFO, usually people put a 10 meter, 50, 20 meter. I guess this close one maybe 5 meter. So this is high density, and we can do full borehole measurement with one cable. And of course, they're very efficient because you're going to repeat the source, you're going to need to move the GFO up and down and the lower cost. And also, as I said, if we pick the high temperature rating cable, any borehole, even geothermal. And the cable itself is just the glass coating material, and we use a fin. It's a small stainless steel tube cable inside, and you have that's why you can hold in very strong pressure. Now we're doing cable can stand for up to 200 megapascal. Because in our borehole we have 10,000 borehole with 160 megapascal pressure of the fluid. We had a high pressure gas from the borehole. This is GFO array you put down in our cable, which had a continuous fiber inside at the sensor. You do have deploying. You just have a weight bar in the bottom of the borehole, which is tracked the fluid into the horizontal borehole with the mesh. So it becomes much easier operation with you. But GFO is a one piece by one piece you connect the borehole side, one by one, and put them in, take them out, and this is much easier to store them down. And we have done some comparison because this is geophone measurement, this is the fiber measurement. It's different measurement method, measure the same signal. So people will say, are they measure the same thing? So we do some comparison. Here is geophone measure based data set, and 10 meters spacing with stats measure at 1 meter spacing. This is basically the section of the together. Now, fiber is a single component. We don't have 3C cable downhole yet. We have surface 3C dash. But remember, we can compare this here with as well. On 3 component geophone, yes, it's important. Fiber cable, as I said, we have 90-degree issue. But if you have particle movement is like this direction, SH wave, we can measure with the cable. But not SHV. SHV, this one is 90 degrees to this. So we can measure both downward P wave and also SHV with the cable. And we need a very precise comparison. This is a velocity geophone measurement. This is a measure the stream rate, which is a distance measurement. So we do a convert from the dash to geophone for velocity data, then give the comparison. Trace by trace. There are quite a few commercial software now offering this module converted between geophone, dash, and dash geophone. Not that deep. Apart from the wave type measurement, we can also derive the borehole size parameter from borehole data, which is the Q value here. This from geophone, you see, it's a kind of spacing of this correct type. It's almost continuously, but the shape is very similar. We can measure the Q value, we can measure the tar value, we can measure the anisotropy from the VSP data set because they have a different direction of the source come to the borehole. And that is very useful for our seismic data process. Today, if you do Q migration, if you do anisotropy migration, you need those parameters. And borehole gives you direct measurement of Q and anisotropy. So it's more accurate measurement and at the seismic frequency. Laboratory will do rock physics, but we measure at the ultrasonic frequency. There's a dispersion between the ultrasonic frequency and seismic frequency. VSP will measure seismic frequency directly, so we don't need to worry about the dispersion. There's one example we use for CCS, CCUS. It's basically repeat the VSP survey, which had a cable installed borehole with the multi-direction walkway. So the 4D measurement, we can see this CO2 injection and movement at the injection zone time changing. This is like 2 measurement. Walkway survey, you can monitor the fluid movement with the VSP. And we also do crosswire seismic these days, use cable instead of geophone. And okay. And we can measure very high frequency signal because our source in the borehole is caught in the borehole, we minimize the surface attenuation. And this is what we achieve in space. This is for the modeling of this real machine. In certain seismic, we have frequency up to 80 hertz, it's a 500 hertz. The crosswire you can see multiply up to 400 hertz. So we have very high resolution with that image. For very single machines. That's another application is crosswire seismic measurement. Particularly if you have multi-well installed cable, one source in the middle, you can measure multiple crosswire profile at the same time. If I show the amplifier data, this is surface seismic. That's crosswire seismic. The same profile. This is different formation mark. But look at those small channel or samples. You will not be able to see from seismic, but you can see the also. If you develop a field for production, this is what we call the reservoir scale seismic. This is a very coarse scale. You will not see this fine formation of reservoir. You can only see big surface. But the issue was this is very expensive operation, and you can only go 2B for each profile, but it's very good for the field environment, not for exploration. We have done a lot of the kind of joint acquisition project during the last 5 years. But we have cable now. We don't have to remove the geophone many times, repeat the source. Nobody do that for you. Very expensive. But if you acquire 3D seismic survey, onshore, offshore, and you have borehole available in this survey area, you can drop a cable in borehole, recording data continuously while your seismic operation is ongoing, and use the seismic source as your visible source, acquiring both seismic and the base data set. That's what I'm doing a lot of this kind of work, onshore, offshore, and different country as well. This is basically, I showed you before about this borehole seismic parameters, right? Use that one, we can go back and reprocess our surface data. We call the borehole driven processing. Basically, we derive some borehole parameters, and we can do this processing, and everything we can do that and associate calculation, and finally we can do some calculation for seismic parameters. That's the workflow. I'll show some results. There's one case example here. We are doing acquiring a 3D seismic 140 square kilometers. Two boreholes, and this is actually offshore in the shallow water. And we have one borehole cable, one geophone rig. So this is the seismic survey source map. This is the onshore diamond map. This is the L down in this corner. And with these two boreholes, we basically can pick up this part source at the 3D size, 3D based survey. This for segment survey is the source coverage area. We can do both 3D seismic imaging, 3D based at the same time using the seismic source. If I just look at the VSP side, this is for the P01 borehole. This is the source we use for 3D based processing. For P-02, we use this kind of source for processing. There's overlapping, but doesn't matter. It's two different imaging processing of 3D based. We do this much source each survey. And here is actually the L source out of the core. That's the structure map of the reservoir. You see many boreholes over there. It's a mature field. We're looking for additional bypass or missed oil. We have two boreholes acquired with seismic data, joint acquiring seismic. We can derive the Q model from the measurement. We also have three other wells in the area we have done VHP survey before. So took the data of the Q model here, we basically do our installation, the 3D Q model for Q migration. Apart from that, we have also more than 100 uphole survey onshore part here. We will start there. Each measurement we can derive a shallow Q profile. With all those 100 profile will be completion, we can generate a shallow Q model here. And that one is just interpretation. So we have a program called the Q promo. This interpretation, this is the inversion. Find to the model, generate a very accurate shadow Q model of the 200 meters. And this and the other one, we are working together building a complete Q model through the data fusion process. With that, then we can do our Q migration. Now, to show this is a conventional PSTN or PSBN. In this case, we can achieve up to 42 hertz. Same data set, but we add the Q model on the Q migration. Now we're getting up to 60 hertz. We increase the frequency by 80 hertz just by this process with help of the data set. Now, if you look at this visually, the fault lines much more clear. There are a lot more population layer compared to low frequency. This one helping me to find or trace the reservoir along the horizon or along the borehole. If we take a coherent slide of the data, and here's just from the conventional PhD data, we take this 2000 millisecond coherent slide. Same one for Q vibration. Now you can see on those lines here, those are the fault line or fraction line, much more clear than this messed up. This is there, but just not enough for resolution. So with this one, your interpreter can do much better interpretation to evaluating your reservoirs, right? So that's the contribution from borehole seismic to your surface seismic. That's why now we quite this kind of work for client. This is our newly developed basic processing workflow. Before, conventionally went to outgoing wave imaging, basically reflection wave imaging, just like seismic. Same as the BSP, but now we can downgoing wave migration and multiple migration. So we can enlarge the imaging area from upgoing only to a full wave view. So this is what we developed. Some example here. Okay, this is one example just did lately. We have a 3D seismic survey at the 70s from the source. There's more available at the 3,000. And we put the table in there and combine data together. So this about 11,000 shots in the code. These are the acquisition parameters for surface and for speed. Now, with this acquisition, we have an old seismic for the last stage seismic data processing result. We make the shape, basically we want to compare with the 3D DSP. So this one we have for now we have those formation top, we identified. This data set at the frequency of this green line up to 53 Hz. Now we took the newly acquired surface site data, we run global driven processing of the same data. I say it's only this new data, but it's surface site we do global driven processing, we can increase up to 75 Hz. You can see initially there's a lot more energy or high energy here. Then we took the basic data set itself, we did a 3D wave migration. Now we can achieve up to 85 Hz. So you can see there's a lot more detailed high resolution image. It's one way application. So with this one application, we can generate different product. Now, if you look at interpretation part, this is basically look at the fault zone identification. So the curvature attribute. So this is maximum positive curvature in the lattice seismic. And this is the overall enhance the process result as the 3D speed. You see a lot more being generated. We do some interpretation here. You can define the fault zone and the sub-fault zone much more clear than from this one. And if you look at the seismic profile here, this is let's say this is the enhanced processing that is speed. So that's why we can now say a lot more sub-seismic features can see from this high frequency data. That's just the mark of the formation and the tracing the reservoir image along the profile. If I zoom into one profile here, this is the legacy seismic. We're seeing some formation of like this. This is enhanced processing. Now we will see those thin layers here, which is not really needed here. By 3D speed, now it's much clearer picture. There's a breakout the sand channel, and there's a picture as well. We will not say here. When you see the picture, this is old one, this new one, now is very the channel much more clear than before. So using geophysics enhance your science data processing and interpretation, then you can drill more high production borehole instead of being on the dry holes. There's another project with the two borehole acquiring together simultaneously in 2024. And this is basically surface seismic data processing and interpretation for identify the reservoir here. This is 3D not imaging. Then seismic fault. And this is very good for the drilling and the population and the reservoirs. But the step we increase the frequency from 42 Hz of this one to 60 Hz. Come up with this. And if we look at the attribute, here is the basic inversion profile. Just impedance inversion. The surface seismic, we have 3 borehole here. This is the 3D DFOS. And if you see now the layers of the continuity or the population, that sequence must be identified in this. With the implementation here, we put this 3 well together. We can generate this attribute. One of this is it's the continuous sand bodies. Before this is you see that we have a boundary here now. You see the boundary much more clearly defined, and this increasing well, and this actually all reduction. So with this help, you can now more accurately of your field with this one. And if you zoom in, look at the particular reservoir zone, here's some of the formation, but it was not really easily separated. If you were simply a reservoir, you never see like a 50, 100 meter thick reservoir. Usually, take the multiple layers, the sand channels, and this is what you need to. So that's GSP part. Right? Now talking about the monitoring part, which is another application using optical cable. If you do reservoir or petroleum engineering, you involve drilling, perforation, production. That's what you need some of the parameters. So with that part, we have now 3 categories of service with cable. We do fracking monitoring during the fracking operation stage with the fiber optic cable. So we do real-time imaging with the adjustment of the fracking parameters, and we evaluating the result of the formation stimulation. We can also use a cable in the nearby well and monitoring this cross well stream when you are fracking this another well. There's another application using that's our low frequency depth coming in. With the installed cable outside the tubing, outside casing, we can actually do long-term monitoring both the temperature and the acoustic noise of fluid, not seismic. And then we can generate a production injection profile. That's really reservoir engineer kind of work. So here shows we have one cable outside the casing. And with that cable, we can actually launch a lot of downhole engineering work. This is just show you when you set up the bridge plant, drop the ball, and the start preparation, and all those activities generate the acoustic energy at go to the casing, and that's what energy will go to the field. And with that one, data we can check our preparation is okay or not okay. Our pay bridge plant that appropriately is sailed or not sailed. All this engineering parameters can be monitored by the cable outside casing. You cannot measure micro event in this thing because it's too close to the fracking well, too much noise. But we measure additional parameters. Now, stimulation will pumping with over the borehole to the casing, we pumping through the high pressure. We start opening the fracture zone, open fracture, and make this unconventional reservoir more produced, more productive. Here is what we measure with the acoustic noise. This line here, each line is one perforation, one bullet. Before we do microseismic monitoring, if you're familiar with that one, we do one stage, 100 meter. We look at the event distribution, growing up. But we cannot see the individual perforation performance. Here now we see, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 11, 12 perforation in this section of this zone. And when we started fracking, you notice this rule here. This 3 perforations not be open. Energy will open this section here. So acoustic noise continuously constantly improve. And this is the timing. This is the location. So now we stop the pumping. We put this temporary blocking agent in there and the problem in there, and we put pressure again. Now those open one will be temporarily closed. The pressure goes to here, also those one open. So through several cycles, you can open all those structures, all the perforation, you get a very high percentage of fracking result, which enhance your fracking operation result. Here we measure both that's DTS. DTS is a measure distributed temperature sensing, the same cable, but when temperature changing, the cable will change because the glass will have a high temperature will be expand, low temperature will be shrink. The same as acoustic, but it's a temperature. So we do distributed temperature sensing, measure temperature along the borehole on every perforation. Also measure noise. So the software you can combine temperature and acoustic noise together, give the interpretation of your production profile on each perforation. Here's some of the result. Here's the temperature and acoustic noise. With that joint interpretation, we can derive. This is one stage with 1, 2, 3, 4, 5, 7, 10 perforation. It's different stage here. Each perforation based on the acoustic noise and the temperature, we can derive a technique production profile, injection or production profile. In this case here, this section was zone 1 at the 3 perforation, 4 good one, but the other 5 not very good. So with this evaluation, you can actually be the focus of the whole different stage of fracking operation will start. And then you modify it and then improve it through the different cycle of operation. Before nobody knows this, just say average response of the whole section. But now I can see the individual perforation performance or contribution to the production. Here is an example. We have a very long horizontal borehole and we have 27 stages of the fracking. And then we start from this end and with the initial measurement, and then we can go back and redesign our fracking operation parameters to enhance. In this case, like you have a new design for this several section, and you get a much better performance. Basically, this is like before, this is after. You can say before we don't get this fully open, but now we get very open. So this is something you can learn from the initial and then improve the background. Here is a joint monitoring of the fracking operation. This is basically the pumping curve, the timing, root pressure, volume. But you can be model here in the meantime. We can use the table much here, microseismic event distribution. That's our geometry. In the meantime, we can derive each operation profile. Another application we talk about is frac heat. If you're familiar with this term, it's a new thing a couple of years ago. You have a treatment profile in the fracking on this well. You have a cable on this well or this well. You have all the pressures. Now I can use the cable this well monitoring this frac heat, which means if you have a fraction zone or hole, connect both wells. The pressure through the borehole fluid, the pumping fluid, can be propagated into this borehole. And the depth in this case is too much pressure. So now we launching this, well, make sure you do family don't damage this well. From simulation, you have fracking this way, there is a fracking zone, the pressure with the fluid will be just like this. Moving along, hit this well and moving away. This is a simulation, this is now the real recipe. You look at the shape, very similar to this and this. So we can see now use the local gas, we can measure it's a slow formation, deformation of the casing. This is an example, we have a real case here. This is a real data set from timing multiple event. From this, what we identified here is this is a fracking well, and this is a motion well. We found that this location we have a strange pressure buildup with very high strain change. And that's from our mission. Then later on, we found out actually there is a case that made this location. We can't get a foot down. It could be squashed. Here. This is the 3 boreholes. This is the one the frac. This is one launching well. At 4,900, the big anomaly here. Stream measurement. It's another one. It responded to this one. So we have measurement, and we actually found out when we load on the tools, well, they're gonna probably start again. It's too cannot be assured with how it's something you measure, and you actually found out this at exact the same location where you have this anomaly. This one will change the production profile, analyze oil gas contribution from this correlation. We have a lot of this from the well in Changqing oil field, and some corporation are producing water, some are producing gas. If it's too much water, the well will not be productive. So now they will do measurement. We find out where exactly water come from. They can block the water here and then increase the production of the gas. If you only produce water, not much gas, you just waste money. So if you can block the water, you only want to produce the gas, this is something worth trying. So this is we do both BTS, gas, and with the joint interpretation, we locate the production of fluids in different population zone, give kind of indication they go back to block the water and enhance the gas production. Here is basically with this long-term production monitoring and also integrate and analyze the logging data with the generative kind of profile or really the porosity saturation at different depths. And then this performance of this result, and you can go back and modify your production program to enhance the oil and gas production. This is we are looking at. Remember, if you do well completion, you basically injecting the cement through the outside casing, come to surface, get the borehole casing and the formation together. Then you have no leakage between formations. Usually, you do this at the operation, then you put a tool in there. It's called a cement evaluation tool measurement. You check quality of the cement behind the casing. Whether it's being properly sealed or there's still gap, have water going through. But now it's cable, you measure temperature because when the cement is cooling down, it is getting heat, right? Heat. So by measuring temperature on the borehole, you can identify or you can check quality of the cementation not on the logging tool. So it's kind of a very convenient. So here is the measurement of the temperature changing, and those are the temperature changing. If they are uniform changing with the cooling together, if there is a mark in the ends between casing and the formation and block the cement into there, there's just part of water in there. So when the cooling down, other part are going high temperature, but this part will be remain the same low temperature. With that temperature measurement, you can do your cementation evaluation, so just cable. So this is basically looking at the temperature change at a different time. And then you can look at this progress and interpret your cooling process of the cement behind the casing with just details data. If you look at how much fluid you put in the borehole and where they went to, this is 3 tests. In this case, you have a 500 cubic meter fluid in the formation through the perforation, and these are the acoustic signal measured timing depths. When you increase to 3,000 cubic meter here, that's why we have similar more noise, where the fluid went in, and more noise, the timing. And we increase to 3,300 cubic meter, and that's noise. So now you know where your fluid went to when you increase the injection to the measurement of the continuous around the borehole, the timing, and then you know your performance of your injection profile. So the many places is injecting and producing from the well. So, but where the water went to, are the uniform pushing the oil away or in the go on the different paths? This will give you some idea of injection operation. And we have a lot of this gas storage in China. Winter time they're using gas for heating, but summertime they put the gas back at the storage. It's called the gas storage field. So there's 2 issues. One is we injecting say 1 million cubic meter gas. Where they went to, are they still in the same place or would we move it away? Can we recover it? Or the other one is the integrity of the borehole, injection borehole. We have cement and casing. If you do this many times, you get damage to the casing. Cement could be cracked, broken, and the casing or production tubing will be damaged. So with the cable measurement, you can measure the temperature, noise, and you can know your borehole conditions. It's still in good condition or it's been damaged. But you don't want to get leaking to the surface. You have to make sure all the injection will have good condition. So all of this thing can be measured with cable, also measure the pressure using cable as well. There's not continuous, not distributed. It's discretized the pressure measurement using optical pressure sensor. Okay, that's the major part I talked about. So the quick conclusions. From that, seismic data offer the key advantage of low cost, high density, and the full well coverage and the high temperature resistance. BGP delivers the solid dust-based survey to clients for different applications. Thus, we provide a high efficient, high density data at a lower cost with superior resolution versus seismic and see some result, right? With very high temperature imaging. Armed cable being hot on the well enable fracture monitoring, where integrated the gas DTS and low air gas, difficult to gas, and the mindset monitoring. So BCP is offering gas DTS service supporting reaching that. Completion production monitoring for integrity, manipulation, low profiling. So this is basically here is the seismic. Here is basically production engineering for monitoring purpose. So how long have we talked? Long enough. Okay. Basically, give you a very quick introduction about optical sensing application today in the world. But we've been also doing a lot of things other people doing, and when experiment and some real production data you can see today. If you're studying seismic, focal seismic is something now we can do with PE, with cable. If you're studying reservoir engineer, there's additional tool can use. Before they have electronic sensors in borehole, measure the parameters, but they are in discretized location. You will not see the detail of your fracking operation, your production profile. They have a tool called the production logging tool. You can generate production profile, measure temperature, something, the spin of the spore. But with the cable, it's a lot more easy, lower cost, and repeat the measurement and continuous because the production logging tool, you have to stop production run and tool, do the measurement, and they do next time every 6 months. This you do every day. Of course, big data volume processing, but there are software now being developed to platform. AI introduced continuous monitoring data processing. The last year, Petrobras of the $10 million project developing a passive seismic data processing package, AI-based. So they have 4,400 4-component optical OBC in the seafloor cover new production field. I think that's installing this year, next year start production. So with this deployment, they will do 4D seismic survey every 6 months and every year. But between, they continue recording passive seismic data 24 hours a day, 7 days a week. And there's about 7 terabytes data come from 44 channel, 4400 channel system, the computer. If you work with computers, you know 8 terabytes really can't by your brain or eye to see those AI-based can do it. So they actually had $10 million upfront video software. Then they have some tests, then they're going to use for production. And this is the first time actually for such large scale continuous monitoring. Okay, that's all I want to talk about this today, and hopefully you'll get some rough ideas. Of course, there are a lot of things I skip out and move forward. I'm not an optical sensing guy, I'm a geophysicist, so I learned that myself. So, but I guess most of you are not optical sensing guys, so I don't get into detail about the optical sensing, the instrumentation design, but for applications, that's why we have a tool. We do the measurement and we do the interpretation, and then we help the whole function. All right. Any question you may have? Yes.
I have one question. How big is the resolution for measure the temperature changes in DFOS while injected flow?
Okay, there are different instruments or interrogator. The cheap one in China, you can with $10,000 you can buy DTS interrogator. They have a 1 degree temperature resolution. The high-end one we ordered was $50,000. They have temperature resolution 0.015 degree. Because they have those, one of the horizontal bore is producing 1 ton of the borehole fluid. 1 ton seems a lot, right? But if you divide it by 86,000 seconds, every second is only very little dripping. That dripping has very small temperature change. So you have to have very high sensitive DTS to measure temperature. So borehole measurement, particularly in that case, you need to get high end. So it's all depends on how much you want to pay. You pay a lot of money, you get a very, very accurate. We had put this most advanced box from Germany, I think it's 1015. And the tender we are telling is 0.011. We cannot do that. Okay. 600 seconds stacking, and you can get to that 0.0. Because the loading produced that box weight because it's not big demand. So if you do this today for the fire protection, building pipeline, oil tank, they don't use that kind of component. Because they get a fire for high temperature. So high low, that's what they need. But for borehole measurement and for production profile, you need much higher than DFOS.
Thank you so much.
Yes.
Have you used this technique in geothermal wells?
Geothermal? We have not done ourselves, but we have looked at a lot of applications in the US. Utah is quite popular. What we can do now is we can deploy a cable, outside casing, outside tubing to continue monitoring temperature, and then identify if there's any potential problem in your production well. That's what they did in the US. The only difference is you have to buy the temperature, the cable is then 350 degrees C. But now they are doing this what they call the ESG system, enhanced geo system. With a very hot rock, you drill a borehole, you put water in there, you frack the rock, and In Europe, they generated rich scale force, rich scale earthquake, and they had shut down because of the dangerous. But a lot of people now using this. Before using this electronic sensor, well, you don't have continuous measurement. Cable you measure every inch, basically, in your geothermal production. Yeah.
Very interesting the monitoring of the practice process. So then you are seeing the fluids moving. For how long should you record them?
Oh, continuous. Okay. We have this guy, he is working in the field. We have this one platform, 12 boreholes, 6 this way, 6 this way. If you frack the whole well, it takes 2 months. So we have a cable there, box sit there 24 hours a day, continuous recording, processing. Even the shut down, the pumping, you still can record it as an event. And the fluid moving, so you just continue recording. Yeah, we have people, particularly for offshore drone acquisition, it's 2 shifts, 12 hours a day. Guys who can watch the instrument recording, watching data instead of any problem. Next 12 hours shipping. Yeah, it's
Okay, thank you.
that's why you need to have a long-term measurement and continuously can look at the problem. If you just do every day after day, you miss the thing.
But then you just see, I guess, you see also the direction where the fluid is moving, right? As you showed in the 2 words, but you need to look to see where it is going with the focus.
Well, the microprocessing events usually is the 3D distribution. You know, the height, width, and the volume. This one, if you have a multi-well cable, you do microprocessing event monitoring, you get the same result. But when you have the cable outside this fraction well, you cannot record it. Microprocessing is too noise. But you measure temperature and fluid noise. So we get an idea of this particularly this well, this perforation, whether it be open or not open. And how much water coming in. But when the water went to, no, you can't do that. You can do 4D seismic, maybe 4D VSP, but not with just acoustic noise of the fluid. There is another service BP is offering EM. EM monitoring fracking operation from the surface. Okay, you have a source, EM source in the surface, you have a 3D distributed receiver, and you do EM survey continuously when the fracking operation. The water went into formation, open the shell formation below resistivity. So the resistivity volume growing is where your water went to. So that one we believe probably better than microprocessing event. But microprocessing can be happen, the rock can be fracking but not connected the fractures.
But then how did you measure that is open fraction? That's something that I.
Well, that's what I say. When the water goes into here, must be connected to fracture, right?
Yes.
So there is a SRV, still the rock volume, and the ESRV. We haven't seen this, 5 million cubic meter SRV, but not much production because many fractures are being connected. It's happened, but not connected. But now the parameter called the ES, the effective still rock volume, that is why they compare the very close to production. So EM measurement, if you have a fracture not connected, there's no water coming in, the receiver is in here. If connected, the receiver is going.
Okay.
So we do, different way to looking at this, but the EM is looking for large scale, not the each individual one, but the section fracking with this low resistivity volume grows is tied to your fracture connectivity and the fluid injection. People even put this salt into the water, you can measure, or they actually want to put the resin coated proppant. And of course, when you coat the resin into proppant, they lower resistivity, you get a more accurate measurement. So it's
Great. Thank you very much for sharing that.
Yeah, so I have another question. How low has to be the low frequency measurement in order to measure accurately the fracture in a tested well?
This is a continuous measurement.
Yeah.
What we start is, before you start fracking, you do a measurement, start already. Not baseline, but a continuous, so you can see the event coming up when you start fracking the formation, perforation, pumping fluid. So this is all continuous measurement. It's for days, weeks, months even. Now, for this low frequency, what happened is when you have two wells, this cable here, you are fracking this well. And this perforation, the fluid come in, there is a fraction zone connect two wells. The pressure carried by the fluid will moving very fast, hit this well. So you have a stress concentration in this particular point. So if you keep pumping at the pressure, you could really damage this casing. In our case, we see the spike of the strain on that location, in two locations, and we have problem down, which means this is the deform. But this deform is not like this. It's very, very slow. So we developed low frequency depth, we can measure to only 1 millihertz, which is 10,000 seconds, one cycle change. If you don't have low frequency depth, you will not see that. But if you go 1 this is say a millihertz signal. 1 hertz cycle, you will not see that. That's why you have to have different box to do this monitoring.
Great. Thank you.
Yes.
Okay, I have a question. Do you know how was this phenomenon discovered in the state?
Okay.
How was this phenomenon discovered?
Discovered, or in the history.
Yes.
That's a new read some books. Fiber optic cable has been discovered 60 years ago. One of the guy got the Nobel Prize for developing the fiber cable can do this kind of work. So this is a long history of fiber discovery. But to use it for geophysics, I think I read the literature. I mean, that measurement started 50 years ago as an experiment. Really started using in the oil field is 2012, maybe now 10, 12 years ago, started really using the field. But DTS is a long-term measurement. DTS is much easier. Because no coupling issues, you can transfer heat through air, through liquid. So borehole deployment of fiber cable for temperature measurements more than 15, 20 years ago. But that's acquisition, if you look at industry, I think first paper maybe 2010 experiment. So that's DTS first, that comes second, now being used for geophysics. So this is actually relatively new study here. If you look in conventional seismic geophysical, there's no DTS, that's measurement. But now people start adding in, so it's quite new.
And I have a final question. Well, what controls the horizontal length that you can cover while monitoring or doing a sensing in a vertical or?
No, VSP is if you know conventional VSP, basically there is basically rule is if you have a 1,000 meter borehole depth, your offset source is 2 kilometers, your reflection from here to the surface is 45 degrees. So that what imaging basically is 2 kilometers, 1 kilometer. So that's your data coverage. Your imaging is half of that. So that's the conventional technique. And now you can do very large offset. Deep well, large offset, you can see large area. So it's proportional to depth of the bore. But now horizontal borehole we do something different. We do VSP on the vertical part of the cable. And this part, we move the source along what's called the work above VSP. We can have basically like a geophone to the horizontal borehole, source on the surface, and with reflection from the below the borehole to the borehole. So it's called the work above VSP. It's all dependent on orientation of the cable here. So there's no fixed number, it's really dependent on borehole depths and the orientation of borehole as well as your offset. So if you keep it well like this, your reflection on this side can be much wider because the reflection comes this way. On this side, your source coming in, reflection going on, but not recorded by the cable, you get a very small action on this side. The vertical wire horizontal section is uniform to cone. But in the deviated wire, you get more on this side and less on this side. That's why we're developing multiple imaging to expanding the imaging area. That's how we do imaging.
And is the cable able to differentiate where, well, the direction of the source?
Yeah, okay. If it's vertical cable, one cable, horizontal formation, the microsite event will not be located precisely. It's on the ring, because from here, same distance arriving in the cable, you don't know where they come from. In the vertical cable, horizontal formation, this is very special. But if you have a curved cable, the event here happens here and here, right? Symmetry to the cable. But on this part here, also here, so you have in this side is a separate event, but in this side can be joint event. So with even the cable, you can pinpoint your microsite event. That's why in borehole is three component GFO. But we don't have a three component cable yet, so we are using either multiple cable locating event or deviated curved cable locating event. It's going to happen between here and here, if there's a cable here, right? But if you have multiple measurement, this event from this 5 point is going to be joined here, but over this side is in 5 separate things. So you know this side, not on this side. So it has to be a curved cable or more than one cable. Then you can pinpoint the microsite event location. So much. So. Any more questions?
You showed information about several projects, let's say big projects developed by petroleum companies. But related to our conversation of the possible cooperation, do you have any examples or experience with, let's say, small projects at university levels where people use your equipment and your software, but just for academic purposes?
One good example is we just did one job here early this year, right? He was the guy in the field. It's a small 3D seismic acquisition. How big is the area? The seismic survey area. How big is the source area? Or the surface seismic? How many square kilometers? 6 square kilometers.
Yeah.
So we have a 6 square kilometers 3D seismic survey. We put the cable in the borehole. We did the acquisition of seismic and the 3D VSP. That data set belongs to the client here. If you talk to them, you get data set, you can do processing yourself. We already convert the data from stream rate to velocity, just like a GFO code. But the only issue, I think the source is not uniform because it's onshore, you will have a problem with gaps. But it's a very good way to handle the process, test it. One of your people here was interested in buying an interrogator from us. But I talked to them today and said, well, there's no funding right now. But something maybe you can think about is to get a box, cable is cheaper, and then do some measurements. Or you want to start looking at data, you have data available from local survey. If you convince the company, right now I think the Schlumberger is doing processing for them. So we did the acquisition, the client give data to Schlumberger for processing of the 3D VSP. But that data, you have agreement with the oil company, can take a look at the. It's just like a normal 3D VSP data set, because we already convert them into a shot gather. We did a continuous recording, because we don't know when the shot starts, so we just recording and output the file every 10 seconds or 20 seconds. Then we take the shot information, XYZ coordinate, timing from GPS, and we sort data, we separate it into shot gather. So you have basically shot gather the raw data we give to the client, and that one's very good for students to play around. That's the first acquisition in Colombia. So it's the history problem. We have a two system here. We are working with different clients. Hope we can do more projects in this country. Colombia is doing conventional VSP using geophone, but we try to use cable here. Something maybe worth to look in the well. Started talking to different oil company from tomorrow, next 3 days. They can push in more projects. But the university welcome to join them with research purpose, get some data, do some study. There's service you can do, conversion. You can do this data conversion from the stream rate measurement velocity. You can separate data from continuous recording to shot gather, and from that you can do. Now, a lot of things need to be done because the cable measurement has special noise. If the location of borehole, between a vertical borehole, the cable is not catching the casing properly, you get a ringing noise, and that has a special way to remove it. So there's quite a few patterns on that removal technique, and there may be different modules, software module developed just for that data processing. We did a project for Saudi Arabia, now they developed quite a few different modules themselves to process in that data. In the geophone, you've been processed for 100 years, they have many functions. But that's something new, people are still working on, learning. That's all I know from this country, but other countries they have. But if you are interested, there is, if you have a group here in the US, there are quite a few public data set available for students to use. You just go on and download it, and you start develop some algorithm, method processing if you want. But for locally, I think someone acquired in India so far.
Okay. Yeah. Thank you very much, behalf of our department and the National Investor Forum. Would like to express our gratitude for your time, for your disposition to share your knowledge. Thank you very much.
You are most welcome.
Thank you. Thank you.
So,